Okay, grade 12 chemistry. This is video number 3. It's about advanced Lewis structures. We're going to talk about some really weird Lewis structures today. We'll start off though with a review of just normal Lewis structures, just basic Lewis structures, stuff you would have seen in grade 11. And then we're going to talk about the weird stuff like overfilled and underfilled octets. Then we'll explain how that can exist with this concept called resonance. And then we will do a bunch of practice with drawing Lewis structures of polyatomic ions. So to begin with, I'm just going to take away this, and we're going to review basic Lewis structure stuff. And the essence of this is what happens when two nonmetals meet. A classic example would be, say, oxygen, which has 6 valence electrons, and we can predict that by looking at our periodic table. Oxygen's over here, 1, 2, 3, 4, 5, 6 valence electrons, and let's say we've got some hydrogens around. Right, hydrogens around. What's going to happen, of course, is that these guys are going to share. Right, the oxygen is going to pull on the electrons from the hydrogen is going to pull on the electrons from the oxygen, and the same thing will happen here. Right, and we draw this as a Lewis structure like this. Where each bond represents these 2 atoms that are in this sharing arrangement, in this tug-of-war kind of arrangement. And so that's 2 electrons, and that's 2 electrons as well. And both atoms feel those 2 electrons. So this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. It sees 8. It's got that stable full octet. And this hydrogen sees 2. That's full for hydrogen because it only wants 2, because it's in that top row. And this hydrogen is also happy, it sees 2. The reality of this, now that you know about electron shells, is a little bit more interesting. And what happens is, if you think about what oxygen actually looks like, you've got 1s, 2s, and 2p. 1, 2, 3. 1, 2, 3. Oxygen's got full 1s, full 2s, and 4 electrons in 2p. Right, if we look at it, right, 4 electrons in 2p, because of the p block, that's 2p, 1, 2, 3, 4. And that makes it look something like this. We've got the S shell, there's 1s, right, that's 1s. If I grab a different color, here's 2s, it's bigger, that's 2s. And then you'll have, I don't know where my blue marker went. Blue marker's around here somewhere. And then you'll have your p orbitals. There's an up and a down, there's a left and a right, and there's an in and an out. Right, there's an in and an out. So theoretically, this oxygen, there's my blue marker. Theoretically, this oxygen has 2 electrons there, 2 electrons there, 2 electrons here, 2 electrons here, and 2 electrons here, 1 electron here, and 1 electron here. Okay. And if that were true, we'd expect it to make 2 bonds, which is fine, 2 bonds. But we'd expect that bond angle to be exactly 90 degrees because these are 90 degrees to each other. But what we actually see is the electrons spread out in a cloud. So the theory goes, when the hydrogen comes in, which just has a single s orbital, right? There's this kind of mutual interaction here, this pull for electrons, and it changes this arrangement. It changes this through a process called hybridization, where these orbitals start kind of getting weird, right? And they get weird, and they turn into these hybrid orbitals, and you end up with, instead of that, you end up with this 2sp3, which actually has 4 spots. And it ends up looking like this. Sorry, the oxygen on the oxygen side of things, it ends up looking like this. 1, 2, 4, 5, 6, 1, 2, 3, 4, 5, 6. Those are the 6 from S and from P, right? These 2 plus these 4. And then so these are now equivalent, and they spread out evenly, and it ends up actually making a symmetrical molecule where you've got the 2 hydrogens pulling on it, and that pull changes the electrical configuration. It actually changes the type of orbitals that are possible. This is something called molecular orbital theory, because now it's a molecule, and molecules have different orbitals. So molecular orbitals, you have the oxygen in the center. You still have that 1s, right, that 1s. But now, instead of having the 2s as a sphere and then the 3 different 2p's, you actually end up with this one's kind of going backwards. You end up with 4 equal sp3 orbitals, and two of them are full of oxygen's original electrons. 2 of them were half full, and then hydrogen would have come in with its s orbital and contributed the other one. Right, so that's where the Lewis diagram actually comes from. It's this hybridization of the oxygen, and when we draw it like this, we're actually drawing attention to that fact. The fact that there are paired electrons, there's the paired electrons, 1, 2, they don't want to bond, but then the unpaired ones are sharing with this hydrogen, and it's all even. It means that this bond angle is not 90 degrees, it's actually 109 degrees, 105 for water, for reasons that will become abundantly clear very soon. So that's molecular orbitals. For you guys, what do you care about in terms of molecular orbitals? Well, I'm not going to ask you how they form or anything like that. It means that bonds and lone pairs will spread out evenly. Around a central atom. Basically, it means that they'll spread out evenly around a central atom according to various principles. So that Lewis, it basically provides the explanation for why Lewis structures are actually helpful. Even though we now know that there's all of this orbital stuff going on. So that's basic Lewis structures. You can do a couple of different ones. Let's try CO2. If you take CO2, you've got carbon 1, 2, 3, 4. You've got oxygen 1, 2, 3, 4, 5, 6. Got another oxygen 1, 2, 3, 4, 5, 6 valence electrons. I get that from the table, of course, right? Oxygen group 16 has 6 valence electrons. Carbon group 14 has 4 valence electrons. That's where that comes from. And then we go, okay, well, that wants to bond because they're unpaired. And this, I'm going to change this. That wants to bond because it's unpaired. And so we end up with this Lewis structure that looks like this. And don't forget the unpaired electrons. So that's also down to hybridization, because if we think about what carbon should look like, carbon should be a 1s 2, a 2s, 2, and a 2p, 2, right? It shouldn't be making 4 bonds if we stick with this, but because of that hybridization, because of the molecular orbitals, it can make 4 bonds. There's some complicated stuff going on there. That's a review of basic Lewis structures. We're going to jump into some overfilled and underfilled octets and try to explain that in terms of electron arrangements. So I'm going to pause and get to that. Okay, so we're back to it, and I'm going to talk about overfilled and underfilled octets, meaning that the octet rule isn't necessarily always accurate. For example, BF3 is a thing. BF3 is totally a chemical that exists. And if we try to do a Lewis structure for it, we've got the boron, which has 1, 2, 3, right? Because it's in group 13, it's got 3 valence, and it's, it's got 3 electrons. And the fluorine, each of which has 7, if you look at the periodic table. I think you can see where the Lewis structure is going, right? It's going to bond like that, so we predict a structure that looks like this. All right, we predict a structure that looks like this. Why is this weird? Well, remember the octet rule, This boron is only seeing 6 electrons. 6 electrons. And yet, this substance exists. We can create it, we can test it, and we can prove that BF3 is a thing. In fact, BF3 is very useful for chemists because it really wants electrons. It wants to steal electrons from other things. So yeah, BF3 is a thing. BH3 is also a thing. So that's an underfilled electron. Even weirder is something like beryllium dihydride, BeH2, which is a covalent compound. And beryllium has 2 valence. Now if we look at beryllium here, 2 valence, because it's 2. And hydrogen, right? Hydrogen. So, that can only do that. So you end up with a similar issue where the beryllium dihydride has only 4 electrons and not a stable octet. So that's a perfectly acceptable structure, even though it seems to violate the octet rule. The octet rule is predictive for a lot of common elements, but it's not necessarily predictive for others. The other thing is overfilled octets, and the classic example of this is something like H2SO4. Sulfuric acid. And what that looks like is you've got sulfur here. You've got sulfur, and we want 4 oxygens around it. Right, 4 oxygens around it. Four oxygens around our sulfur. There's also hydrogens, right? There's a hydrogen on each. And what's essentially going to happen here is kind of funky, so bear with me. This oxygen will bind to that hydrogen, and this oxygen will bind to that hydrogen. This oxygen retains a bond to the sulfur. And then these oxygens, theoretically, they shouldn't be able to do anything. This sulfur is happy. It's got a full electron shell. It's got 8 now. So it should be, SOH2. But this oxygen has a very, very, very strong pull for electrons. It's got a strong electronegativity. So it's got such a strong electronegativity that it'll actually pull on that lone pair. And same with this oxygen. It'll pull on that lone pair. And what you end up with is the true form of sulfuric acid, which looks like this. Right. So see if you can figure out why we call this an overfilled octet. An overfilled octet. Think about which of these atoms has more than 8 electrons that it's holding on to. And you'll see very quickly that it's this sulfur. It's got more than 8 electrons. So it's got 1, 2, 3, 4, 5, 6 bonds that it's seeing. That means that there's 12 electrons. Right? 12 electrons on that sulfur. How can this be? How can the sulfur make a bond with 12 electrons? Well, the reason for that is, if you look at the keep in mind, all of the electron orbitals are available. The lower ones are just more likely. And sulfur over here, being in 3p, it has access to 3d. It can promote to 3d. So it can actually store those extra electrons on the bond in those higher energy orbitals. It's a higher energy state, so it's not, super nice for the sulfur, but the high electronegativity of the oxygen stabilizes the whole system. And that's an overfilled orbital. So this is overfilled. An overfilled orbital. Another classic example of this is actually one that was first created by a Canadian. This is Neil Bartlett from UBC. And he created this compound, XEF4. It was the first noble gas compound. And you go, well, how can that happen? Noble gases don't react, right? They already have a full octet. What's going on? Well, the same thing happens as what happened with that oxygen and the sulfur. The fluorine is just so strong. The fluorine is just so strong as an element, as an electronegative element. It wants electrons so badly that it can actually just split up this lone pair and pull on those electrons so hard that you end up with a Lewis structure that is very, very weird. Right? It's xenon with 4 fluorines on it. The fluorine has a full octet, because that's why it pulled so hard, and the xenon still has these 2 lone pairs because they didn't get touched. So this xenon is feeling 1, 2, 3, 4, 5, 6, also 12 electrons. It's overfilled. So basically the octet rule isn't the be-all and end-all of chemistry. You can have structures that absolutely break the octet rule in all kinds of weird ways. One more that I will show you, but please don't take this one to heart because I'm not going to ask you to draw any of it, is this guy. And this guy is profoundly weird. Trihydrogen ion. It's got a charge of +1, and it's got 3 hydrogens and 3 bonds in a triangle. But if we think about what it means for a hydrogen with a +1, this is hydrogen, hydrogen, and hydrogen. To get a charge of +1, which we do observe, that means one of these electrons had to leave. So this is a compound that has 3 bonds with 2 electrons. 3 bonds with 2 electrons. So what the heck is going on there? Right? Theoretically, 3 bonds should have 6 electrons, but this thing is doing it with just 2. So this is some like forbidden chemistry. This is some really weird stuff. Essentially, the electrons just spend a lot of time being shared amongst these hydrogen ions, and each hydrogen is really making kind of half a bond at a time. And so the fact that you've got three of them each making half a bond matches the 3/2 kind of bond character that they're exhibiting, and it's profoundly weird, but that exists in chemistry. This is in fact the most common molecule in interstellar space, because there's a lot of hydrogen out there and it can exist like that. So that brings me to the next topic, which is resonance in polyatomic ions, which I will explain in a second. I'm just going to pause, and then when we come back off pause, I'll get into that. Okay, I'm back off pause, and we're going to talk about resonance. So resonance, the evidence for resonance comes from studies into the shapes of various molecules. One of the easiest ones to explain is ozone. So we know that ozone is O3. And we know it's a neutral molecule that has this structure O3. And the only way to do that is to take 3 oxygens, and what you would have to do is essentially double bond one of them, and then single bond the other. And what you end up with is this interesting structure where kind of this becomes its own electron pair, and that electron just joins into the single bond, and that ends up looking like this. Right? Like that. It's a profoundly weird structure. Right? That's a weird structure. The reason it's a weird structure is oxygen likes to make 2 bonds, but here we've got oxygen making 3 bonds, here we've got oxygen making 1 bond. And here we've got oxygen making 2 bonds. But from experiments, we know that ozone is bent, and we know the other weird thing that we know is that both of these are the same length. So same length. From experiment, the same length, which is strange because double bonds are normally shorter than single bonds. So double bonds are shorter than single bonds. So what's going on? Well, this is where the concept of resonance came in. Resonance. Resonance structures come from the fact that when we assigned those electrons to ozone, we could have assigned them in 2 ways. We could have assigned them like this, or we could have assigned them like this, right? And both of these structures are acceptable. Both of these structures are acceptable. Right, we've just swapped the double bond from one to the other. And so the theory goes, because they are exactly the same length, no matter how often we measure it, they're always the same length. And because we know it's bent, there's this resonance structure where it's constantly flipping back and forth between the two. And so this is called resonance because they're flipping back and forth, It's also called electron delocalization, or a delocalized electron. So a delocalized electron. Basically, that electron gets shuffled back and forth between the two oxygens, and it reduces the formal charge on each one. What do I mean by formal charge? Well, here's another way to draw it, is you kind of have a dotted line. It's almost like a 1.5 bond. And you'll end up with something that looks like that. What I mean by formal charge is, remember that oxygen likes to make 2 bonds. So this guy is making 2 bonds, it's fine. So we call that a formal charge of 0. This one, though, is making 3 bonds, right? It's making 3 bonds. Now, normally that's what nitrogen does. That's what nitrogen does, which is, 1 proton back. So this oxygen basically has a different number of bonds than it normally would. That gives it a formal charge of +1, and this a formal charge of -1. Formal charges are a way to keep track of what's formal charges we keep track of like how stable the atom is, how close to its true bond character it is. This one's got 1 electron, 1 full electron more than it normally likes to have, because normally it likes to be like this, but now it's got an extra electron here. It has to make 1 bond instead of 2. This one is making more bonds than it should, so it's got a formal charge of +1. On this side, it's the opposite, right? This is the +1 and this is the 0. So these are just constantly flipping back and forth between the formal charge. At the resonance structure, though, what you end up with is this thing has a formal charge of -1/2 kind of thing. This one has a charge of -1/2, and this has a formal charge of +1. So still neutral overall, but it's a more stable structure than this, because they can just shuffle that electron back and forth, a 1 electron going back and forth, that delocalized electron. So that's how resonance structures can stabilize a polyatomic compound. We see it very, very often. For example, you might know that SO4 is a compound, right? SO4 well, we saw sulfuric acid earlier. SO4 can be thought of as sulfuric acid that has lost the hydrogen but kept the electron. So it looks like this. Like this. Okay, it looks like this. And the minus charge is held on the this is held here on the oxygens. That looks bad, but remember that there's a resonance structure happening here. So what's really happening is it's more like this, where you've got 2 electrons kind of shuffling around between the sulfur. So there's really a 1.5 thing going on. So it's really more like -1/2, -1/2, -1/2, -1/2, and the whole thing then together has a charge of 2-. So it stabilizes the polyatomic ion and keeps it as a block when it's going through reactions. So that's where polyatomic ions come from. Now the last piece of our note here is drawing the Lewis structures of these polyatomic ions, and there's just a certain set of rules for that. So we're going to try to draw a few of them, and I'll teach you the rules. I'm just going to pause and set stuff up. Okay, we're back off pause, and we're going to draw some polyatomic ions from scratch. This is directly from the curriculum, but I had to go through all the other stuff like overfilled and underfilled octets and resonance in order to help explain what we're about to do. But there is a simple method that works really, really well to predict these things. So we're gonna go with that. So let's draw some complicated Lewis structures. We're going to draw one that's near and dear to everyone's heart, nitrate. We're going to start with nitrate, which is NO3-. NO3-. And there's a procedural method to drawing these structures that works really well, and that's up here. First, we have to count up all of our electrons. So we have a nitrogen, we have an oxygen, 3 oxygens, and we have a minus charge. So that's what's here, NO3-. And then we have to look at our table to see how many electrons we have. So nitrogen has 5 valence electrons because it's in group 15, 5 electrons. Oxygen is in group 16. Group 16, it has 6 valence electrons, so 6 electrons, but there's 3 of them because there's 3 oxygens. That's 18 electrons. And we have that negative charge, and the negative charge means we have 1 extra electron in our molecule, so that's 1 electron. So when we add it together, 5 plus 18 plus 1 is 24 electrons in this molecule. So we've learned how many electrons we have. The next step is over here, bond. So we have to choose one to be in the middle, and then we bond it. Typically, the one that's at the start is the one that's central. So we'll go with that one first. So nitrogen in the middle, and then we bond around it. So we have 3 oxygens to distribute. We just put the 3 oxygens around. And they have to be attached because this is a molecule and it stays together, so we're going to attach them. Like that. We're going to attach them. So that uses up 6 of our electrons. That's already used up 6 of our electrons. Right? 1, 2, 3, 4, 5, 6. So that's 6 electrons in the bond. Six electrons in the bond. Then the next step is to make the outside atoms happy. They've got the higher electronegativity here, so they're going to like the electrons more. So what we do is we just fill in the outside atoms. If we've used 6 electrons, that means we still have 18 left. So we actually have enough to fill up all of those. That's 6 electrons. Each pair of electrons here is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 2 is 18. So we've got 9 electrons. So we've got 18 electrons in lone pairs on the outside. I got 18 electrons there. Together, that makes our 24. Right? That's the 24 electrons that we started with. So we're good on the number of electrons. And then the last piece is fix inside atoms. Note, fix the inside atoms. This nitrogen is not happy right now. Why isn't it happy? Well, the octet rule is still a pretty good rule. So instead of this structure, the way to fix this is we can move a lone pair. From any one of these lone pairs we can choose, and this is where the resonance structure comes in. We choose any one of these lone pairs. I'm going to take this one. I'm going to take, say, this lone pair, that lone pair, and I'm going to turn it into a second bond right there. So instead of drawing it like that, I'm going to draw it like that. And I chose that oxygen completely arbitrarily. I could have chosen any one of those oxygens. And indeed, the true story here is that it's like a third of a bond on each oxygen, making that resonance structure that stabilizes the nitrate. So that's nitrate. Nitrate looks like this. And it's got a charge of -1. We can also assign formal charges to these guys. Right, this oxygen has a formal charge of 0 because it's okay. This oxygen has a formal charge of -1. That oxygen has a formal charge of -1. Nitrogen normally makes 3 bonds, but it's making 4 right now. So if we look at, imagine these electrons are these bonds are kind of cut in half. 1, 2, 3, 4, with 4 electrons in the valence plus the 2 underneath makes 6 with 7 in the center because nitrogen has 7 protons. This gives it a formal charge of +1, and -1 minus 1 plus 1 is -1, so it matches our true charge. You can kind of predict these things using formal charge as well. If you look down in the description, I've got a link to our virtual textbook that's talking about formal charges. You can learn about them as well. They're a handy tool to check your work to make sure that you are actually in the lowest formal charge mode for your polyatomic ions. Okay, that's nitrate. Let's try something kind of related is nitrite, right? Nitrite. NO2 minus. You might be wondering, why NO2 minus? Why is that a thing? Just the same as NO3 was. Well, we do the same thing. We count electrons. Nitrogen has 5 electrons. Oxygen has 6 electrons times 2. And the minus means that we have another electron. So that's 12 electrons. So 5 plus 12 plus 1 is 18 electrons. 5 plus 12 plus 1 is 18. So I have to put a little 18 electrons around our atom. Next step, bond, right? Bond. So we put our nitrogen there. We're going to just one bond. That's using up 4 electrons already. Then we're going to fill up our outside atoms, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We filled up our outside atoms. We filled up our outside atoms, but we haven't used all of our electrons. If we look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We've used 16 electrons in blue, right? But we want to get to 18, right? We want to get to 18 electrons. So we have 2 more electrons that we can play with, right? 2 electrons gives us our 18 electrons. Where do they go? Well, the outside ones are happy. We can put them in the center, right? We have put 2 electrons that we can stick in the center. That's part of fixing the inside atom. If we have extra electrons, they go to the center. And then the last piece here is looking at this central atom to see whether it's happy or not. So that's to you guys. Is it happy? Take a minute to think about whether this nitrogen is happy with what it's got right now. The answer is no, it's not happy because it's currently seeing 1, 2, 3, 4, 5, 6. It wants to see 8 electrons. So what do? We do that promotion trick. We take this lone pair, the entire lone pair, both electrons, and we turn it into a new bond. We turn those 2 electrons into a bond. Remember that a bond is a pair of electrons. So the true structure of nitrite is something like this. Now, of course, this is a resonance structure, so it's going to look something like this. It'll be flipping back and forth between these 2 forms. Right, flipping back and forth between these 2 forms constantly, back and forth, back and forth, back and forth. But you can just draw something like this, and the resonance structure is kind of implied. If you want to get fancy with it, you can do the dotted line thing. You'd be like, this is nitrite, like that, with a formal charge of -1/2 on each side here and a formal charge of +1 in the center. Yeah, so that's drawing advanced polyatomic ions. There's a bunch of them. We can do all kinds of different ones, all kinds of strange and wonderful ions. I'll have a practice sheet that you can try, so please try that out, and then I'll have answers to that practice sheet up on EDSB. So thank you very much for paying attention, and I'll see you guys in class.